Okay, think about your morning routine for just a second. You wake up, and you probably immediately tap a little glowing rectangle to turn off your alarm. Then you swipe up to check the news, maybe you pinch to zoom in on a photo, and you tap out a quick text message. We do this hundreds, literally sometimes thousands of times a day, and we do it totally on autopilot. But today, we're going to slow things down a bit. We're going to intentionally peel back the layers of this super mundane routine to look at the absolutely extraordinary engineering and, honestly, the subatomic physics happening right in the palm of your hand. Because the invisible world sitting right beneath your fingertips, it is far more complex than you probably ever imagined. I mean, really stop and think about that premise for a second. Every single day, billions of us are just touching a perfectly flat, solid, unmoving piece of glass, right? There are no buttons to click, there are no physical switches to flip, zero moving parts, and yet somehow this cold, inanimate sheet of glass knows exactly where your finger is resting, down to the millimeter. It knows how long you're pressing, it knows the exact direction of your swipe, and it translates all that physical human intent into a digital action in a fraction of a millisecond, faster than you can even blink. It honestly feels like magic, but it's actually this incredible symphony of material science, electrical engineering, and just raw processing power. So, how exactly does it pull off this illusion? Section 1. The evolution of touchscreens, from air traffic control to smartphones. So, to really understand the glass in your pocket, we need to take a quick look back at how human-computer interaction actually got here. Because, fun fact, touchscreens didn't just magically appear out of thin air when Steve Jobs unveiled the iPhone in 2007. The journey is actually a decades-long saga. We can trace this all the way back to 1965. That's when an engineer named Eric Johnson over at the Royal Radar Establishment in England developed the very first finger-driven capacitive touchscreen. And he built it specifically to help air traffic controllers manage their super complex radar systems. Fast forward to 1977, and researchers at CERN, the massive particle physics lab in Europe, they started building their own screens because they needed to control thousands of variables in their particle accelerators, and they didn't want to build a physical control panel the size of an actual gymnasium. Then, in 1982, the University of Toronto cooked up the first human input multi-touch system, though it used this really bulky frosted glass panel and a camera. For decades, this stuff was just strictly for massive industrial machines or clunky early PDAs. It really wasn't until 2007 that the tech was finally miniaturized enough to revolutionize mobile phones, rescuing us from those tiny, frustrating plastic keyboards and moving us into the era of pure glass. Section 2. Resistive versus capacitive screens. The war of touch technologies. Now, if we want to understand modern screens, we've got to talk about the two warring factions of touch technology that really fought for dominance. On one side, you have resistive screens. If you've ever used a slightly older ATM, maybe a grocery store checkout screen, or an old GPS unit in your car, you know what a resistive screen is. They always feel kind of squishy under your finger, right? And that's because they're basically just transparent mechanical keyboards. They have a flexible plastic top layer and a rigid glass bottom layer with a tiny, tiny air gap in between. When you push hard enough, you're literally bending the plastic down to touch the glass and complete an electrical circuit. But man, they have drawbacks. Because you're looking through layers of plastic, the screen always looks kind of dim and muddy. Plus, all that physical bending causes a ton of wear and tear, and they really struggle to register more than one touch at a time. Then, on the other side, we have capacitive screens. This is what's on your smartphone right now. No squishy plastic, no physical pressure required at all. It's just a rigid, lightning-fast piece of glass. Instead of needing you to physically mash two layers together, it relies entirely on electrical proximity. So it completely solved the friction, the dimness, and the wear and tear problems just by getting rid of moving parts altogether. Section 3. The invisible electrical grid. Peeling back the glass. Okay, so if your phone isn't relying on you physically squishing layers together, what's actually happening in there? Let's literally peel the onion and look at the microscopic layers of a modern device. If you sliced your phone screen in half and threw it under an electron microscope, it is definitely not just one solid piece of glass. It is a highly engineered, microscopic sandwich. First, on the outside, you have the protective glass. That's what you're actually touching. Right beneath that is an incredibly thin, totally transparent, conductive coating. And this is where the real magic is. It's usually made from this fascinating stuff called indium tin oxide, or ITO. ITO is a huge deal in material science because it pulls off this crazy paradox. It's fantastic at conducting electricity, but it's completely see-through. It is literally a wire and a window at the same time. Below that ITO layer, you've got microscopic insulating layers, and then an inner layer of conducting glass. These layers are so thin and so perfect that the light from the display just shines right through them, keeping your screen crystal clear while hiding this microscopic electrical secret inside. Now, the way these materials are stacked brilliantly illustrates a fundamental concept in electronics. What we just described, two electrical conductors separated by an insulator that doesn't conduct electricity, is the exact textbook definition of a capacitor. A capacitor's entire job in life is just to store an electrical charge. By sandwiching that conductive indium tin oxide between layers of insulating glass, engineers essentially turned your entire phone screen into one giant, transparent capacitor. It just sits there, quietly holding a steady, invisible electrostatic field, kind of like a perfectly still pool of water or a really tightly stretched rubber band. It's just sitting in suspended animation, waiting for something to come along and disrupt its balance. Section 4. The science of conductivity. You are the missing link. And this brings us right to the biology of it all. Because that electrostatic field, it's waiting for one very specific thing to interact with it. It's waiting for you. See, to an electronic device, humans are basically just giant walking bags of salty water. Because our bodies are packed with water, dissolved minerals, and salts, we are highly effective electrical conductors. We actually carry our own slight electrical charge. So because you conduct electricity, when your finger gets super close to the screen, you don't even technically have to press on the glass. You are simply introducing a massive new electrical conductor into that delicate electrostatic field. When you do that, your finger literally steals a tiny, totally imperceptible bit of the electrical charge right out of the screen. The charge has basically found a new path to the ground, and that path is you. You become the third element in this system, sucking away electrons and altering that invisible field just by hovering near it. To actually take advantage of that stolen charge, modern screens use a very specific tech called mutual capacitance. Think of it like this incredibly dense, totally invisible spiderweb stretched right across your phone's display. This web is an X and Y grid of highly conductive traces made out of that indium tin oxide we talked about. And these traces are small, like way thinner than a single human hair. The horizontal rows and the vertical columns cross over each other thousands of times to form this grid. But because there's a microscopic insulator right at the intersections, they never actually touch each other. Now, the battery is constantly sending these high-frequency voltage pulses rapidly down the horizontal rows. Meanwhile, the vertical columns are acting like sensors, just listening and detecting the baseline voltage at every single intersection. So together, this invisible spiderweb forms thousands of individual tiny capacitors at every exact point where a row and a column cross. So here's exactly how the trick works in real time. The horizontal rows, the x-axis, they're the transmitters. They're firing off electrical pulses, scanning the entire screen line by line at blinding speed. The vertical columns, the y-axis, are the sensors, constantly monitoring the electrical charge at every single intersection. Then, in swoops your finger. As soon as you touch the glass, your body absorbs a tiny fraction of that charge. Instantly, the sensing column detects a sudden voltage drop at that one specific intersection. Boom. That data is immediately sent to a dedicated microchip called the touch controller. And this chip is working overtime, okay? It doesn't just do basic math. It has to run really complex algorithms to filter out electrical noise from, say, the fluorescent lights in your office. It has to ignore it if your palm accidentally rests on the edge of the screen. And it has to find the exact mathematical center of your squishy, imprecise fingertip. Once it filters all that out, it matches up which row was firing and which column sends the drop, and it instantly calculates your exact X and Y coordinate. Just to give you a sense of the sheer scale of this, even an older, standard definition screen with a basic 3:4 ratio has over 1,564 of these intersecting touch nodes on its grid. Modern HD smartphones, they have thousands more than that. Every single time you quickly tap your screen, your phone is checking every single one of those microscopic nodes all at once. It's literally performing millions of silent, complex calculations every second, just to figure out which little app icon you wanted to open. To put that in perspective, your smartphone is doing exponentially more math in 1 second just to track your thumb than the navigational computers on the Apollo spacecraft did to get humanity to the moon. And this grid design solves one of the biggest problems with the old tech, because the mutual capacitance grid is constantly tracking thousands of independent intersections all at once. Instead of just waiting for one physical circuit to close, it gives us multi-touch. That's the ability for the screen to track 2, 3, or even 10 fingers at the exact same time. Without this invisible grid, the gestures we literally take for granted today would be physically impossible. Pinch to zoom, that changed user interface design forever. It allowed developers to build these fluid environments where you can rotate a map with 2 fingers, swipe between apps, or literally play chords on a digital piano app, because the controller chip is seamlessly processing all those individual touches at the exact same time. Okay, so let's pivot for a second and apply all this subatomic physics to a highly relatable real-world annoyance. If you live anywhere with a real winter, you know this struggle for sure. Picture this. You're waiting at a bus stop in a blizzard. The wind is howling, you've got your thickest winter gloves on, and suddenly you get a super important phone call. You start furiously tapping the green answer button in a total panic, and absolutely nothing happens. You tap harder, you press with all your strength, but the phone just completely ignores you, and the call goes to voicemail. Right? We've all been there. So why does that happen? Industry folks actually call this the glove problem, and it perfectly proves the science we just went through. Remember, capacitive screens literally do not care how hard you press. They only care about electrical conductivity. Materials like wool or leather or ordinary synthetics, they are amazing thermal insulators, keeping the heat trapped near your hands. But crucially, they're also highly effective electrical insulators. That thick material completely blocks your finger's natural electric field from ever reaching the screen's field. Because there's an insulator blocking the way, that invisible grid doesn't register any drop in electrical charge at all. So the controller chip just assumes nothing is touching the glass, no matter how aggressively you poke it. The elegant fix for this? You've probably seen those winter gloves that have a little patch of different colored thread on the fingertips. That's highly conductive metal thread. It acts like a bridge, grabbing the electrical capacitance from your skin, carrying it straight through the thick fabric, and delivering it directly to the glass. Section 5. A world at your fingertips. The macro impact of microgrids. So let's zoom all the way out from the microscopic grids and conductive threads, and just look at the macro impact on society. Because this one technology has completely reshaped our physical world. The ultimate superpower of a touchscreen is its adaptability. It's a total chameleon. On a phone, it goes from a typewriter keyboard to a number pad to a video game controller in a fraction of a second. In high-stakes environments, like a hospital or a military command center, operators can just drag and drop assets right on a screen without messing with a mouse. They're in ATMs, self-checkout kiosks, and obviously, they absolutely dominate modern car dashboards. Which is funny, actually, because back in the late 1980s, cars like the Buick Riviera actually tried using early touchscreens for their climate control. It used this glowing green CRT monitor, it beeped really loudly every time you touched it, and people absolutely hated it. The vision was there, but the capacitive tech just needed a few decades to catch up. And today, smooth glass displays are just the standard in pretty much every new vehicle. And when you contrast the physical limitations of old tech with modern screens, this massive societal shift makes complete sense. Think about a regular computer keyboard for a second. It's got over 100 fragile plastic keys, 2 metal contacts under every key, little rubber springs, exposed circuit boards, and all these massive gaps where dust and crumbs and coffee can just fall right in. It is a highly complex machine with hundreds of moving parts, which means there are hundreds of different ways for it to eventually break. But a capacitive touchscreen, 0 moving parts. It is just a solid block of hardened glass that makes it incredibly weatherproof, really hard to vandalize in public, and super durable. Plus, for places like hospitals or busy restaurants, a perfectly flat piece of glass is just incredibly easy to wipe down and sanitize without ruining the electronics inside. That durability and hygiene is exactly why they've completely taken over. We have moved incredibly fast from a world built on mechanical gears, clicking buttons, and physical switches to a world where silent, invisible electrostatic fields hold our entire digital lives together. So I want to leave you with a final thought to chew on today. The next time you grab your phone and unlock it with just a single effortless tap, remember what's actually happening. Beneath that perfectly smooth, cold piece of glass is an invisible, microscopic web of conductors quietly performing millions of complex electrical calculations every single second just to connect you to the rest of the world. It isn't magic. It's just a breathtaking achievement of human engineering. But if we've managed to turn a static piece of glass into a lightning-fast extension of our own minds in just a few decades, it really begs the question, what seemingly impossible invisible interfaces are we going to be interacting with next? Thanks for exploring the invisible world right beneath your fingertips with us today, and, as always, stay curious.